how can I use the fundamental theorem of calculus to evaluate integrals? Well, let's remember back to what the fundamental theorem of calculus actually says. Well, here's the statement of the fundamental theorem of calculus. I got that function little f from the closed interval to the real numbers, and it's continuous. And I've got the function big F, which is the accumulation function. It's the integral from a to x of f of t dt. That's the definition of f of x. And then big F is continuous in the closed interval, differentiable on the open interval, and the derivative of big F is a little f. In other words, an antiderivative for little f is big F. What is it that I want to calculate? Well, what you don't really want to calculate is this. I mean, who really cares about big F, right? The only thing you really care about is the integral from a to b of f of t dt, right? You only really want to calculate big F of b. Who cares about big F of x? This sort of trick comes up all of the time in mathematics. To understand an object in isolation, to understand big F of b, it's necessary to fit that single object into a family of objects. In this particular case, you're right. I don't care about big F of x, but I want to calculate big F of b. Right? I want to be able to integrate from a to b f of t dt. And by fitting f of b into this function f of x, I can then try to understand something about f of b. Because I know how big F changes. I know that the derivative of big F is little f. So what do I know about the accumulation function big F of x? Well, I know that big F of a is equal to 0 because it's the integral from a to a of f of t dt. So I know the value of big F at a, and I know how big F changes. I know that the derivative of big F is little f. And now I'm trying to calculate big F of b. So I know that big F of a is equal to 0, and I know something about how big F changes. The change in big F is related to little f. That is enough information to recover big F. So before we recover big F, let's try to walk there in steps. Let's first suppose that I've got some function big G, which is some antiderivative of little f, right? So in other words, I mean that the derivative of big G is equal to little f. Well, how does big G compare to big F? Well, I also know that big F differentiates to little f, right? So I know that big G's derivative is little f, and that's the same as the derivative of big F. So I've got two functions whose derivative is the same. What does that tell me? Well, by the mean value theorem, that means that big F must be big G plus some constant. What's the constant? Well, the other fact that I know is that f of a is equal to 0, right? This is another fact that I know about big F. And this fact, and the fact that big F of x is big G of x plus c, is enough to recover the constant big C, right? If big F of a is equal to 0, that's also G of a plus c. So what does c have to be so that if I add it to G of a, I get 0? Well, this means the constant big C must be negative G of a. Well, now we can put it all together. So this fact and this fact then combine to give me that big F of x is big G of x minus big G of a. So does that help at all? Yes, this solves all of our problems. Remember what big F of x was. Big F of x was the integral from a to x of f of t dt. And what this formula is telling you is that this integral is some antiderivative for little f, evaluated at x, minus that antiderivative evaluated at a. And this solves our original problem. The original problem that we wanted to answer was just the integral from a to b of f of t dt. And that, by substituting in b for x, is big G of b minus big G of a. But we wouldn't have been able to understand this had I not fit this specific problem into a whole collection of problems. Integrating from a to x allowed us to understand this particular integral from a to a specific value, b. Well, let's change the names around and summarize what we've got. So here's how this is usually summarized. Suppose I've got some function little f from the closed interval a to b to the real numbers, and I've got an antiderivative of little f that here I'm calling big F, but before we were calling it big G. Anyhow, then what do we know? Then the integral from a to b of little f, which you remember before I was calling this little f of t dt, just so I didn't confuse my variables, but now I can call it x because I don't have any t's here. The integral from a to b of f of x dx is that antiderivative evaluated at b minus that antiderivative evaluated at a. We started off with a formulation of the fundamental theorem of calculus in terms of the accumulation function. But now we've got this new formulation of the fundamental theorem of calculus. Makes it a lot easier to see how we can use the fundamental theorem of calculus to evaluate integrals. Evaluating an integral is the same as finding an antiderivative and evaluating that antiderivative at the left and the right endpoints, taking the difference.